digital part, electronics and fluid dynamics in the first half. And post lunch, we have one session on optical simulation by Avinash. And this will be a 1 hour long session followed by a short break before we can reassemble again at 4 o'clock for panel discussion. So I welcome you once again, and let me see.
Hi, Avinash.
Yeah, hi Avinash. Just checking the people who have joined in. Yeah, we can start, Avinash. So the speaker for this session is Mr. Avinash Padmappa, and he's the lead application engineer for Optis products at Ansys, and he's specialized in domain of light and ADAS. Avinash has been working with Ansys for the last 5 years and has 10 plus years in the lighting simulation industry. He is responsible for providing technical assistance for VR applications, lamp design, ergonomic assessments from different industries such as automotive, consumer goods, and so on. He did his master's in industrial and automation and robotics from VTU Karnataka. So I welcome you, Avinash, and I hand the session over to you.
Thank you, Avinash. Uh, Hello.
Yes, Avinash, I can hear you.
Okay. Um, Good afternoon, everyone. Thank you for having me in today's session and for this opportunity to present. So, I'll, yeah, sorry. So, today I'll be speaking about the optical simulation and the ADAS topics, which are, I mean, it's becoming more of mandate in the current design process. So every OEMs are adopting, and it's not only automotive, but even the other industries. It could be unmanned vehicles, it could be aviation, or the different applications. And so I'll take an opportunity to introduce to this topic and also show how the HPC is being adopted, why it is so important, and how it is leveraged. So basically, you have heard about the different physics. Is sorry, some background noise. Okay, thank you. So you have heard about the other sessions yesterday and today from CFD from structures. The topic I'm covering here is on the optical. So this is another physics in Ansys portfolio, and we also do multiphysics connecting with CFD and structural. But today I'll be more focusing more on the optical simulation alone, and basically to show how the the interconnected platform and the material informations are leveraged here, and how we can achieve the more realistic product by using the simulation techniques. So let's start with optical simulation. The very first topic, just to introduce what we are trying to bring in here, is basically it's a science of vision, um, generation, propagation, and behavior of light. So either in terms of perceived quality of the buyer or the customer is going to visualize the product, but also in the point of the camera, lidar, radar, which are all around the same frequencies or around the frequencies, how these sensors are going to perceive the world around us. And finally, within the system, if I'm emitting a light using LEDs or the bulb, how it is propagating through the system. So it could be a very simple headlamp, it could be a turn indicator or a mood lighting inside the vehicle, or it could be any display or a phone or any functional lights we see. So application is big. Um, any lighting systems or any illumination we can address in this particular topic. So what are the areas we are covering is starting from design through the imagination. When I need to define to my supplier what I should get with the intensity of the light, the light distribution on a given area, the way it is going to interact with other materials in the surrounding. Uh, if I can get a better idea of these at initial stage, I can build a very good RFQ for the supply of the material, and then engineer can work on achieving the desired product. So this is what we call it as virtual manufacturing, considering all the light leakages, the efficiency, and the performance in terms of achieving uniform illumination, meeting the regulation, homologation requirements, and how we can make sure that the product with components coming from different suppliers is pursued as a homogeneous for the customer or the buyer. So to give some idea, to achieve a product like here, where we are innovating different ideas. So there's a simple tail lamp, but using off mirror, we are trying to give a multiple reflections, like a halo effect, and it's completely giving a different visualization. So they should meet the regulation very first instance, and then the visualization from the different view angle. So tail lamp being 1 meter to 1.5 meter above from the ground, a standing person should get a very good visualization. Same way, the driver following the vehicle should also see it as a functional requirement. So this is basically achieved through running a ray propagation calculation on a optical property and considering different light sources. So it could be an LED, it could be a OLED, the different types of sources we use, and performing the photometry, colorimetry, and if it is in visible light range. But if you are working beyond that, we are talking about radiometry simulations, and also see how the human eye is finally going to perceive this kind of product. So to give better idea, every company wants to try out different ideas at the same location, components with different ideas and different illumination, when it is functioning, when it is not functioning, and with a different price range, different technology adoption. So to give it a very good experience. So this is something we can try out virtually. So doing the same thing with physical prototype would cost a lot of money, time, and any modifications will be restricted again. So with this background, now I'll explain like what are the challenges will be facing when we are working on this kind of simulation, and how the HPC would be an advantage for every companies. So for example, here I'm looking at the light guide of a stop lamp, and so this is a dual function lamp. Functioning with a low power and the high power as a uh, when headlights are on, so there is a position lamp, and then when it's braking, so then we have a stop lamp conditions. And uh, there are two factors here. One, the illumination should be uniform throughout the light guide. So the LEDs may not be there right behind this. It could be at one corner. So there are different ideas again. And we'll be using some diffusing materials so that we distribute the light from a point source to a wider area. Still considering the contours, the curvature, the illumination may not be very uniform. And also there are many mirror surfaces around this as a bezel, as a reflector, which could also reflect some portion of the light. So this could be a light leakage, the unwanted light, and how to visualize those and see whether it is going to be um, an issue in either in terms of regulation or in terms of pursuit quality. So that is something we would like to check. So when we run the simulation for this particular lamp, we identified 5 areas where I want to study in depth whether it's acceptable or not acceptable. So that could be a reflection at the plastic parts or the bezel areas, and this could be acceptable based on how much light we are measuring in this area. So I really want to measure very accurately in this location. So if I run simulation in the software, basically we are just talking in terms of taking a photo. So you take a photo with 10 megapixel camera or with a 20 megapixel camera. The informations are captured more in a higher pixel cameras. So this pixel is per square inch, how many information the photo can be captured. The same way here, when we run the simulation, I'm going to break up this area into millions of pieces and try to have a the light information in all these areas, so that when I measure, I'll get a better distribution information. So this would require a huge computation again. So if I'm using a simple workstation with 4 core quad core processor with say 8 GB RAM, so the simulation time would take about 12 hours or even overnight, like 14, 16 hours time. But I want to see the result in an hour, and to achieve that, we do the back calculation considering the amount of rays we are emitting and the number of cores I could achieve. So keeping 1 hour as a timeline as a target, when we did this calculation, we found out that we would need around 4,000. I mean, this is really not 8 hour simulation, but this was around 24-hour simulation for this particular lamp. And when we did the calculation for this particular lamp, we targeted around 4,000 cores on an HPC, so that I can every 1 hour I can get a new result. So any modifications I do, change in position of the LED, change in material type, material parameters, or it could be a geometrical modification. So we would like to see how it is improvising the design. So then we can run many iteration, so that when I make a proto or when I go to the production, my product is more accurate. So now you already heard about the different type of adaptation. I mean HPC, moving from a smaller cluster to the HPC cluster, and then supercomputers or the huge HPC clusters. The simulation time again um, can be saved much higher. So I'll come back to this slide. As we also see here, the software methodology. I mean, here we are following Monte Carlo mechanism, and it's a ray propagation. For every ray emitted from each LED, it will calculate the ray propagation path, and whenever it interact with the material, it will calculate the transmission, reflection, absorption calculations, and see how much ray will finally converge towards the area of interest or the area of the sensor. So this is quite scalable, and the scalability is quite linear. So with that, we can achieve a very a big advantage in terms of the simulation time with any additional course we are bringing in, and the software is completely supported on that. So now going further, we are also offered now in Ansys Cloud. So Ansys POS was newly added into the Ansys portfolio about 4 years back, and we have been, I mean, we have been working on the product enhancement to make it available as part of the Ansys Cloud, and it can be deployed in any other cloud platform as well. So I'll just quickly play this video. So Sorry, I don't have any music in this. So definitely the advantages of the cloud, getting a result update on the go. So it could be in your phone, in the tab. We can get an update continuously, and any variations in my requirements. So I would need 50 cores sometime. I might need 500 or even 2000 or 3000. So we can scale up and accommodate based on our requirement. So the cloud is much versatile in terms of offering. So now the other important topic, or the most required enhancement, is on the GPU side. So as GPU is becoming more and more affordable, and there is a very big enhancements happening in this area. And also, since we work on ray propagation calculation, which is quite typical to the GPU computation, we could able to enhance the GPU availability in the market. So currently we are in beta stage for this product. We are running tests on different type of graphics available, but it's currently available in NVIDIA graphics card. And the biggest advantage, as I'll show you more details in the upcoming slide, but it's quite scalable again from the different graphics card like RTX to A4000 or A6000, and the performance is much higher. And also there is another feature which we are offering, is called live preview. So usually what happens, I run simulation, I try to save the details of every path the ray has taken and the energy it has reached in the sensor location. So we lose a lot of time in saving these informations into the hard disk for every calculations I make. So with GPU, we could also able to make a modification where my interest is to see how my product is going to look even before I make any major modifications or any changes, so that I'm really not looking at saving my results and documenting it for further. But at initial stage when I'm working, I want to make a very quick review. So this is made possible with, again, thanks to the GPU technique, and we can run simulations from hours to minutes. So within a minute, you'll start getting the result. It could be noisy, and the longer I keep in the same orientation, I could I could get a very good result going further. So with this technique, we have done various benchmarking, say for exterior light, and again we have different solvers like direct and inverse. I mean, in a simple word, the direct simulation is basically light emitted from LED to the sensor or to the camera outside, whereas inverse is for the ambient light. So the light coming from the environment, passing through the lens to the optical system, and again coming back. So basically, we run simulation in a two different ways and combine the result to get a the lit condition when the lamps are working, and the unlit condition when lamps are not working, but I'm seeing them like in the street or in the showroom. So the computation techniques are different. The efforts are different again for these type of solvers. And also we are benchmarked for car interior simulation, where the plastic is huge. The field of view is big, and then we are talking a lot about the reflection studies here. Whereas in exterior lighting, it's more on the transmission, or if it is a simple reflector based lamp, then we also simulate on the reflections. And also for the interior and the high quality products like a perfume industry or a watch or any jewels. So as I said, like the applications are enormous, and um, what very important for us is the number of triangles we have for each component. So when we work on a CAD product, CAD component, and when we save the result, we will be doing some tessellation, like a triangulation on this geometry, and that will be used for applying the material and calculating the solving all the equations. So the triangulation is quite important for us, and the higher the triangulation, the simulation time would be more, and it also defines how complex is the details in these components, and also the number of sources. So for each source, each LED, the equations will be solved. So if I have 10 source, then it's 10 times. So with these calculations, when we did the benchmark, we can easily see from P6000 to GB100 or RTX, um, the 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 multiplications are like it's 2 times from P6000 to GB100, and it's close or little more than 2 times for RTX 8000, and it's the same way for RTX A6000 as well. And it's a similar trend we are seeing with the different solver with a different type of source. So with few modification, because the transmission calculation takes more time than reflection equation. So we have certain variation depending upon the physics we are solving, but the trends are quite clear. With the investment we make, we could get the results much faster. So with this slide, I stop on the optical simulation. Now I'll switch over to autonomous vehicle or the ADAS. And we heard so many things about the camera simulations and um, so many companies like Tesla, or it could be Google, or many other companies developing their own autonomous vehicle or autonomous car and using different sensor mechanisms. And the most important is to give a confidence to the users or the customer or the approving authorities, the agencies, uh, that the sensors or the all the mechanisms in the vehicle work in all the possible conditions. And then we have fail-proof plans. If some sensor fails, then what vehicle is going to do. So then we need to make sure that we give this kind of confidence. So achieving that confidence is quite important, and what mechanisms are being adopted, what industry does, and where the effort going, and how we are again supporting that with HPC. So I'll speak about that in the coming slides. So maybe to just start with very quick introduction on the levels of autonomy. So already hearing about these terms. The Indian OEMs or the vehicles available in Indian market are talking about ADAS enabled vehicle, and what does it mean, and where are we going with these definitions. So as you can see here at the bottom, the L0 is driver only. Mostly most of our cars available in India are in this condition. So then going about the L1 and L2, where we have some assistance. So the image can also give you some idea. As you can see here, there are three components. So the eyes on the road, hands on the steering, and legs on the pedal. So when I come to the L1, the legs on the pedal is off. And when I go to semi-automated, even hands on the steering wheel is also off, but he's still looking at the street, and he is the guy who is going to control. So the driver has to be there, and he has to be alert as well. So this is where the ADAS system comes into the picture. Whereas when it comes to the L3 and L4, it's a big leap, what we say, where the driver is no more seeing on the street. He might be monitoring some systems, but he can be looking at somewhere else for a few seconds or few minutes. So there's something which software, the vehicle should take care, but he should be alert. But when it comes to L4, the driver can be off for some time or for a longer period. And when it goes to L5, it's completely driverless. So there could be only a passenger, or even if there is a driver, you don't have to look at the driving window. So there are a lot of work happening in this. There is no production L5 available. So L5, more or less, it's going to be a what we call as a geofenced areas, or the area where the vehicle knows how to drive, and it's a closed community, like inside a premises of a office or a campus of a university. So some fixed areas, what we are seeing right now. And the L3 and L4, there are a lot of competitors in the market where a lot of activities are happening. And the challenge is mostly with the sensors and the understanding about working on the sensor information. So yeah, let's take a look about this in the coming slide. And what are the challenges we are basically talking here for ADAS and autonomous system? And basically, uh, the effort is to make sure that we know our challenges and we know how to handle them. So the very first one is on the AI and the software reliability. So we are expecting vehicle to be on its own. So we should know that this is pretty reliable. It does not fail, or we have all the backup plans placed in the system. So the second one is the fault tolerance. So we should know what is the intended function of each and every feature, and at what instances it can fail. So I mean, understanding our system and making it more and more stronger is the main purpose. So we should know what's the fault tolerance, at what instance it can go wrong, or even if it is not functioning, I should know what does that mean. So understanding that is also very important. And all the sensor limitation. So I cannot just live with a camera. I cannot just go with a lidar or radar. So I should know the limitations of each and every sensor, and how we are going to do a fusion of each sensor and take advantage of one on the other. So then on the cyber attacks, which is becoming quite important to make sure that the software we develop cannot be controlled from an external agencies or the external mechanisms, so that the vehicle can go erroneous. So it should be very good. And also all the human factors, especially when we are expecting driver to take control back in L3 and L4. What kind of information we are going to put it back, and if I expecting driver to take control, can I make a lot of sound and lighting so that he gets panic? No, that's not a good idea. So then, how are we going to put the information back, and how much time he will have for to respond back? So all these kind of factors we should understand and deal with these kind of challenges. So very interesting topic. What Toyota president spoke. I mean, this was about 6 years back, and based on the calculations and the way we were evolving, uh, they could able to come up with a number that every vehicle they are going to design, they have to run it for 8.8 billion miles of road testing. And then a lot of deliberated discussions happened, and to find out, do I really need to do this much of road testing? Can we do virtual testing? And how much of virtual testing can be done, and how much the road testing should be done? So there are a lot of work happening on that, and there is a better understanding now on this scenario. But there is still the requirement remains same, whether it's a virtual or a physical testing. So around 8.8 billion or even 10 billion is what we are looking at in the testing side. So this is going to be a very, very big challenge. Even after so many years of testing, Google itself has not even crossed 4 billion. So there's still a long way to say. They know all possible scenarios when their sensor can go wrong, and they know how to tackle those. So that's where the confidences we are talking. And the other important factor is to understand uh, when my sensor can go wrong, and what are these scenarios we are talking about. Do I really know every possible way in different parts of the world? And like we always say, like in India, it could take more time knowing the the kind of the traffic and the behavior in the street. But these scenarios are quite common. So that could be an animal, or it could be just a hoarding, or a person wearing a camouflage and he is in the street. So whether you want to treat it as an animal or a poster or as a placard, how do you consider it, and whether the vehicle should stop or it should wait? So there are a lot of confusions, and how do I make sure that I follow a different methodology to verify these kind of challenges? And it's something we are talking about it a lot with all the customers we are interacting. So there are major bifurcations for the edge cases. So it could be a weather condition. So I could have a lot of snow on the street, snow uh, piled up or accumulated, and then rain, thin rain or a light rain to the heavy rain conditions, or there could be a wildfire and the different lighting conditions and the infrastructure. So that could be a fence, which is very difficult to recognize, the reflective surfaces, the statues, easy to get confused with the live people, and the type of road users. And I mean, there are still the machines are not quite strong enough to make all the decisions. So understanding these is quite important. So currently, there are a lot of efforts going on to identify the edge cases or the worst case scenarios for each and every sensor, and trying to develop perception algorithm which can find a way to identify and make some decisions. So how quicker I can identify uh, and how soon I can make a decision is quite important. So that's where the efforts are going on. So I don't spend much time on this blog, but I just wanted to show you like the kind of approach we follow in the industry. Basically, it's a autonomy stack, what we call, and this is how the industries are working on. And so there are so many blocks, there are so many efforts going on, and any automation in this level is going to save lot of time. And what's interesting is at the bottom you see there is a cloud or the data center compute cluster which is going to support this whole mechanism. So from start to end, every level we need the cluster. So quickly to see what are the blocks we are talking here. The very first block talks about the system and safety. So this is where I basically list down my worst case scenarios or the functional requirement of any activity or any feature. So I want to do a cruise control, adaptive cruise control for my vehicle, and the way it's supposed to work, and what are the conditions involved, and what are the variations in that, and what are the possibilities it may fail. So all these conditions we should define it here. And then based on my system, based on my understanding, I need to define my test space analytics. Means I have to define how I'm going to test my the design I'm building. So I know what are my requirements. Now I did the coding. Now I need to test the coding. All right, I need to test my mechanism. And then there are tools to do testing, and this is more of a virtual testing. And same thing, we can also do it in a real field testing. Like I get a camera, mount it on my vehicle. I attach it to my laptop where I have all my uh, software lying to 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 analyze the photos coming from the camera and see whether I can identify the different objects around my vehicle, and how many frames I take to make a decision, to recognize and to make a decision. So those are the things which we'll be talking more about in these blocks. And then we also talk about drive analytics, and basically the scenarios or the variations, and the country specific requirements, the certifying agency requirements. So everything will be I mean addressing here. So all these feeds it back to my test-based analytics. So my requirement, my limitations, or the minimum uh, testing required, the the, the company specific internal standards or the specifications. So all these we'll be defining here. And then once we do all the simulation, I'll be learning from those and creating my own um, reports to say how much I covered and what's my confidence on my system. So all these kind of things will be doing. And this whole mechanism will be supported by a platform which understand different forms of inputs and the outputs between each domain and make a communication so that any remark I find out should communicate back to the the first and the last step of the autonomy stack. So all these things will be working on. And so this as it said, like there are different departments involved here. There is a vehicle department, the team working on the motors, engine, transmission, the drivetrains, uh, and the software team, the validation team. So every team has to understand their inputs, and then finally they have to roll out their vehicle. So the communication is quite important here. So with this background, let's take a look at an use case and see how we are uh, doing it in our software. And again, how do we compute the millions or billions of kilometer testing, and how industry accept this virtual testing as a valid input to build their confidence. So I'll give a few examples in the coming slide on this topic. And one quick slide just to speak about. Um, we we support most commonly used sensors from radar, camera, lidar, or ultrasonic. So as you see, other than camera and lidar, the radar and the ultrasonic are in a different physics, in a different frequency range, and the way it interacts with the material is totally different than camera and the lidar. And we have physics to support these applications as well. And what are the topics we could cover is basically the component design, like the developer of each sensor itself. So it could be Bosch, or it could be um, uh, I mean, it could be Nokia, or there are many companies which are working on the optical creation, or it could be Velodyne, for example, for the lidar, and again for the radar. There are many companies are working. So all the component developers are interested to improve the efficiency, have a energy efficient chip which works more effectively on for a given specification. So we work on those areas. So then the second level is on the vehicle integration. So I buy a sensor, I put it on my vehicle, and for better visibility, say I keep it behind the windshield, behind the wiping area, so that my camera has a good vision all the time. But the windshield itself will adds certain deviation to the vision. So the photo is no more clear because of the curvature of the lens, and the thickness of the lens will have an optical effect on the image. So how can I understand this problem and make certain modification in my post processing so that I can filter or make a correction? So that's something we can work at very initial stage. So the same way for the radar mounted on a bumper with a metal clamp. So there is a change in RCS plots, and how much it's the change, and what are the possibilities of crosstalk between the different radars in the same vehicle, or the radar in the other vehicles as well. So we can do this kind of testing again. And then coming on to the validation on the scene simulation, basically driving through a scenario, through a virtual environment. uh, that's where the interest is finally. So I want to do I want to run through a city with all my sensors and with a set of vehicles around me as a traffic condition, and see whether I can recognize the each vehicle surrounding, and see what speed I am each of us are going, and what's the gap between the vehicle, and if he brake, can I recognize is braking, and can I stop my vehicle also automatically. So these are the things which I want to test it, and creating a scenario, running through this scenario is what we do. So I have some slides on this topic to speak in the coming slide. So for today, I taken this example. This is L3 example, and so this is called jam end function. So the basic idea is like, say there is a set of vehicles, maybe stop for a jam or at a traffic light, and uh, so the red vehicle is the main vehicle, what you call ego vehicle, and this vehicle is following another vehicle. Both of them are on motion before they come to this jam, and the green vehicle might change the lane till the moment it is designed in a way, when we use adaptive cruise control, the vehicle will be following another vehicle with a fixed distance. So I can fix it a gap of 100 meters or 150 meters, and whether this vehicle increase the speed or reduce the speed, the gap is always maintained. And as per the autonomy principle, without manual intervention, it is not allowed to change the lane. Changing lane is not uh, allowed. So say this is a manual driven, and this person changes the lane looking at the open slots, and this vehicle is exposed to the vehicle in jam or the stopped vehicle. So now the ego vehicle has to stop, and it's a hard stop, and how long it takes for it to understand that there is a jam, and it has to stop. So then there are a lot of variation. So basically we're talking about 13 parameters: the speed of this vehicle, the speed of this vehicle, and the gap between each and every vehicles here, and at what instance this is going to change the lane, and even changing lane can happen much faster or slower. And all these kind of variation, if we consider with a simple math with Monte Carlo approach, we are talking about 39 million iterations in this condition, and that we can bring it down to 28,000 by following a different DOE or the optimization mechanisms, say mathematical regression, identify the sensitive parameters, use multiple forum to detect the failure points, and um, do the probability sampling to to build confidence on that. So so we can follow different techniques so that we run less number of simulation and check whether my vehicle is going to perform good. And this test, we are doing it, say the for one set of sensors. It could be a camera, it could be lidar or a radar. And if there is any change in these sensors or any change in my perception algorithm or the vehicle specification, so we have to redo it everything. So if not everything, at least a certain level we need to redo the simulation. So that's where we are talking about such a huge simulation, and we cannot expect a person to sit in front of a system and do all the modification step by step. So it has to be automated. So how do we do that, and how do we run these simulations is something we'll look at in the coming slides. So let's understand the process. Um, so initially we have two components here. One, the virtual world. So we need a scenario, what you call, and then we need a set of vehicles, different segments of vehicle, and also the variation in each simulation has to be documented or prepared by someone. And then take these inputs, make all the variations every time, create a test plan. So all 28,000 plans here, run the simulation, whether it could be in cloud, it could be in HPC or in a local desktop. So with respect to time, and then do the analysis. So I'll show you at the end how this analysis would look like. Let me give some more idea on each components here when I talk about scenario, the vehicle, and each topic, and how do we manage. So with our products, we basically provide a set of tracks, test tracks, commonly used by various customers across the globe. So, for example, this is from Michigan University. So they have a test track for autonomy vehicle, and for one of the project, we got the laser scanning done. So this is quite detailed scanning, and as you can see, we could apply all the material properties of a asphalt or a I mean every signboard, vegetation. So this looks like realistic, but this is all virtual. The background is just a image what we are embedding, and then we can also bring in the difference between the dry road and the wet road condition and the night condition. So this is quite realistic, and we can build these kind of tracks. We can uh, build digital track as well, and then make it available to any of the companies who are interested to do virtual practice before they come and do the physical testing in this track. So that's the main idea. And there are several methods available to capture any street of any country and create a track like this. So that's the main purpose of having a feature to create the scenarios or the world database. So the second level is on the vehicle dynamics. When I'm trying to replicate the real vehicle, I should have all the vehicle dynamics information captured. So when I brake hard, how much my vehicle will go down or nose dive, and that because of that, the camera vision will be modified, and it might it may not see the signboards on the hanging signboards, or maybe the signboards on the flyover or 5 or 6 feet height signboards. So can I see those kind of scenarios and see this may not be for long. It could be for a few seconds till I brake and leave the brake. But even that could be a critical timing. So how can I see these kind of conditions? So that's where the vehicle modeling is quite important. And when we do the simulation, we follow different um, types of the sensor simulation. So each one has their its own advantage, but also the limitation. So maybe to give you a quick idea, there are three type of sensors we follow. So ideal sensor, stochastic, and physics-based sensor. When we talk about ideal sensor, we are basically um, using a mathematical modeling just to recognize the objects surrounding the vehicle. So usually the output from the software for this kind of sensor is a list of objects. So it know how many vehicles are there in my surrounding, and based on the field of view as a triangulation or as a um the cone or a pyramid definition, it can easily recognize whether the vehicle is in my visibility range or not, and it will give the list of that. So typically here I'm skipping my perception algorithm, and that's why we call it as ideal sensor. And in stochastic sensor, we try to add certain uh, perturbation or the disturbance in the system. So disturbance could be a low light condition, could be a rainy condition or a snow, slippery road. So the different conditions we can call it, and the output is still like a ideal sensor, but it is much better than, I mean, much more informative than ideal. So with the perturbation. So the last one is on the physics-based sensor, which is more realistic. And for so for example, if I'm still talking about camera, camera has four components. So you have optical system, then you have imager, then a post processing. So imager is just a CMOS sensor, like capturing the light and converting it into electrical format, and then someone will do the post processing and convert it into a readable format like a photo. And then there is a perception layer which basically recognizes the objects. So what we do here is we give an output of a imager and then allow you to do the post processing and do the perception handling. So this will eliminate the dependency on a physical camera, um, but we can always give this input back to my perception algorithm and do the similar kind of test as we do it in the reality. So then the options to create the different scenarios and traffic so that I can mimic my real conditions. So for example, here a vehicle overtaking and then is again changing the lane. So recognizing this and see how effectively I can recreate the scenario and see how my vehicle will behave in such scenario is something we can do it. So there are again different ways to do that. Either we capture it from a real video and create a virtual scenarios and then do all the variations within that. If I get one instance, then we can do a lot of variations within this part. So then here is an example to show you. Once we run the simulation, I might have 10 or hundreds of iterations done. And say, for example, here I'm considering all the worst case scenarios um, and select them together, open it and play them at the same time. So then I can see uh, initially each vehicle. So if you see here, so there are three vehicles, and this is the main vehicle, the follow vehicle, and this is a slow moving vehicle. So the idea is the follow vehicle will change the lane, and the main vehicle will get exposed to this slow vehicle, and it has to stop. So in this condition, we can see the main vehicle is at different speed. At an instance, say this vehicle might be moving at a speed of 30 kilometer per hour, 35, 40. The intervals could be a different one. And the same condition apply to the other vehicles as well. And then the vehicle will change lane. This change lane can happen when the gap is either 30 meters or 100 meters. So at different condition, it could happen. And we can see how each simulation went and whether vehicle really stopped or did it fail. So there will be a lot of plots, graphs, output, but we can also see visually how this scenario completed. So these kind of things which we can run. And here you are seeing the braking conditions and the, the the each iteration whether it failed or it cleared. So the green indicates there was no impact, and when there is an impact or passing through the body, it turns red. So these kind of things we can visualize. So then at the end, we can run various possibilities um, with a snowy road, with a evening condition, night with headlamps on, and the vehicle overtaking at different speed. So there are various instances which we are running. And as I told you before, like we can automate this complete process and run it in HPC or cloud um, to run thousands of kilometers in a day. Again, depends on the type of sensor we'll be using. So if it is ideal sensor, I can run for thousands of kilometer. But if it is physics-based sensor, it could take few hundreds because it's computationally rich um, calculations. So this is basically to give an idea about how we run in cloud. So definitely we have a lot of advantages with the cloud where the simulation time is much lesser. We get more computation power with the cloud. So with this, I stop my presentation. Again, thank you so much for the organizing team, and thank you for all the audience.
Thank you, Avinash, for an excellent presentation. And let me see if I have any questions on the chat first.
Okay.
Okay, so there is no question on the chat, but basically a comment that diagram best helpful to understand architecture of a system, probably referring to one of the slides that you had presented earlier. Okay,
Yes, the autonomy stack. Thank you so much.
yes. So Saurav has raised his hand. So Saurav, you can unmute yourself and ask the question directly.
Thank you, sir. Actually, I want to ask a question from the optics side, SPOS that sir has demonstrated just while
Okay.
ago. Uh, my question is that whether this ANSYS SPOS will be able to simulate laser matter interaction in terms of ray tracing models that yesterday Kapil sir was talking about.
Yes, I mean laser we do support, but can you give some more info like what type of application we are talking here? Because there are
Uh,
certain variations within
yes, sir.
that.
Yes, yes. Suppose in case of the laser welding applications, there are keyhole formations. So within the keyholes, those reflection of the light within the keyhole increases the absorptivity of the laser. That is best modeled by ray tracing methods. Uh, that's why I want to know whether the ANSYS SPOS has the capability to simulate such scenarios.
Yes, definitely we do support on this topic, and we have done several study with a few government labs in India, and I think my colleagues who I mean who has specialization in this, he can give you more ideas on again.
So then, if is it possible that from your end you can provide us some support, because I haven't seen people use the people using ANSYS as of now, ANSYS SPOS specifically as of now for this ray tracing simulation, specifically in this laser material processing domain.
Yes. So basically, like within laser, we have two different topics, and if you're talking about wave propagation, then we try to do that with the other product of Ansys called numerical. But if it is ray propagation alone, like you have some mirrors and you want to guide it and do the either it could be
Yes,
etching or a metal cutting. So those kind of simulations we can do it in SPOs, and
yes, sir.
we have extensive material available with Ansys. You can access to that, and definitely can try it on your own with the guided
Okay.
training
Actually,
material.
to know whether this the software or the solver is able to simulate how the rays are being absorbed and reflected by, means that kind of thing. Actually, I was.
Yes, yes. So we are not just doing a photometric calculation, but we also calculate for energy absorption. So you get an output in terms of watt per meter square. So for every material, but still we are not considering the mechanical property of a material. So uh, our information stops on a given surface. Say I'll select a small area of it could be 3 mm by 3 mm or 5 mm by 5 mm, some one small area, and then we do all the meshing over there so that I can capture all the energy absorption happening in that location. Then take this info, take it to the ANSYS mechanical and do the thermomechanical simulation to see how this absorption is happening. Because the advantage here is you are not doing it uniform energy absorption, but you get a the distribution from core to the outer area, and these kind of localized distribution applied on a thermomechanical will give you much better results. So that's something we can simulate, and maybe we can set up another meeting to you where we can show you what kind of work we have done previously, and you can always explore on that.
Thank you, sir. I will be looking forward to it. Thank you for your answer. Thank you, sir.
Thank you. So I shared my email ID at the initials at the first step of my slide. You can always reach us back on that, or Abhimanyu, or we
Yes, yes.
plan to get
So
connected. Yeah.
yeah, so they can write to us, and if there are any, because we had multiple speakers, so let that email come centrally, and
Mm.
depending on which speaker and session it has been asked to, I'll work with them.
Okay.
Okay.
Okay. Thank you.
So are there
Abhimanyu,
any other questions? Yeah, feel free to unmute, or you can also type in the chat window. I'll be taking this up with Avinash.
This is Kapil Devnath from IIT Kharagpur. So I have a question, Mr. Avinash. So
Yes,
in
sir.
this, so recently this numerical, I mean, has been acquired by Ansys, right? So is there any, I mean, has it been implemented in HPC or?
numerical.
Because
I'm
we
not
use it
sure
quite
it. Yeah.
extensively in our research group, and for some I mean simulations we feel the need for going for HPC, especially when we are doing optimization problems. So in that case, so I was just wondering if you can give me some information on that.
Okay. Actually, I'm not a domain expert of that.
Okay.
Maybe I
Yeah.
can quickly check that and we'll
I
get back.
can add something, Avinash, because of we were engaging with one of the accounts, sir. So uh, this particular version, I mean, the one of the earlier version had some issue with scaling on multiple node. I mean, it was scaling on multiple core of a single node, but multi-node there were some glitches. But I think prior to that, till last year, multi-node, multi-core was enabled on numerical, so we were able to get the HPC part. But exact status of the latest version, I'll believe it is 2021 R2. I can
Mhm.
come back to you, sir, on that.
So this is it the same software that we download, or is it a special software that needs to be
Uh,
downloaded
it should be
for?
Ansys numerical itself. But
Okay,
on the
that is.
HPC part, I'll check, sir, whether it is a different HPC, because our endeavor is to club all the HPC together. So
Mhm.
today, the HPC of mechanical CFD as well as the low frequency, high frequency uses the same HPC now.
Okay.
So the moment we acquire, we try to integrate it into Ansys platform. So if it has not happened now, it will happen in terms of HPC also. So I'll check
Okay.
on what HPC it is using, numerical, and also the current status on the scaling part.
And what about the multiphysics part? Is there any integration with other softwares
Uh,
in
yes, that
numerical?
is one endeavor where a lot of work
Okay.
is happening. Yeah. So
Mhm.
let me check on the use case if we have implemented or put anything on the public domain.
Okay. Okay.
So
Yes.
the
Thanks.
latest has been Zmax. Numerical we acquired, but latest acquisition have been Zmax now.
That is the ray tracing one, right? Yeah.
Yes, sir. Yeah.
Okay. Okay. Thank you very much.
I've taken a note of it. I'll respond to you directly.
Yes, that will be great. Thank you.
Sir, one more thing. This, sir, hello.
Yes.
Yeah,
Yes,
hello.
please go.
Yes. This whether this Zmax will be integrated in the future versions of Ansys, or it will be offered as a separate platform. Means to since we are in CIC, we are able to means get updates, regular updates of this Ansys from your team's end. That's why I'm asking whether in future it will be integrated or what.
So maybe I'll try to answer and Avinash can add further. So the endeavor of Ansys is to create a multi-physics portfolio. So even when we are talking about Zmax or numerical, later on you will see multi-physics aspect coming into picture, like if there is any thermal aspect affecting the behavior. And same thing we have been doing with electromagnetics also, high high frequency electromagnetic. We are not now solving any physics in silos. So we are able to do multi-physics simulation. So yes, if you ask me, in principle, it will be integrated, as well as you will be able to couple multiple physics together. And that would be the overall endeavor to increase the fidelity of overall simulation.
Okay, thank you, sir. Thank you.
Let me check if we have anything on the chat. Okay, so I don't see any more questions on the chat either, Avinash. So maybe we'll conclude the session and take a small break. So from 3:30, it's already 3:40. So till 4 o'clock, there is a small break, and we can reassemble for panel discussion, where again I look forward to insightful comments from Avinash. So do join us back at 4 p.m. And thank you, Avinash, for an excellent presentation and providing so much insights into the HPC part as well as the optical simulation. Thank you, Avinash.
Thank you. Thank you so much. Thank you all.
So, sir, the same link would be active for panel discussion. Somebody can clarify.
But I see there is a mail today, which has a different link, right? Or is it the same link?
I believe we are copy pasting because many of the panelists are not joining, right? Few of the
Okay.
speakers are not in the regular session. So it should be the same, but I just wanted
I
to
am one of
understand.
the panelists. I was given the same link.
Okay, okay. Then it is the same link, sir. Yes, sir.
I was given
Okay.
this link.
Okay. So same link is valid. So we'll join again at 4 p.m.
Okay.
Then we'll start the panel discussion, sir.